But before we go into the general space, let's look at a simple, very small example. There are only 4 nodes and 6 directed links. Nodes 1 and 2 points to 3, 3 points to 4, and then 4 points to back to 1, 2, and 3. Okay. Now, what is the intuition of the importance score vector pi, which should be a vector of length 4 here, if we assume that such a pi consistent set of scores actually exist? Here's one particular view. We can think of nodes 3 and 4 as collectively acting like a supernode. Okay, let's call this supernode 3 plus 4. And here's node 1, here's node 2. 1 points to supernode 3 plus 4, so does 2, and the supernode points back. Okay. So now, intuitively, you look at this supernode, you say, this supernode got 2 links pointing inwards, but each of these nodes 1 and 2 only has 1 link pointing inward. So intuitively, you think that nodes 1 and 2 should each has a smaller importance score than the supernode 3 plus 4. And furthermore, by symmetry of this graph here, nodes 1 and 2 should have the same importance score. And then the supernode 3 plus 4 need to distribute its score in some way between nodes 3 and 4. So at least we know intuitively that pi 1 should equal to pi 2, and each of them should be smaller than pi 3 plus 4, the supernode score. Okay. So intuitively, that's what we should anticipate. Now we can write down the math a little further and calculate in this small example very easily the result. Now first of all, you also notice that in this node 3 pointing to nodes 4, that says that basically all the importance score pi 3 that I may get goes into node 4. And node 4 only got this 1 incoming link. Right, so pi 4 should equal to pi 3, or pi 3 divided by 1, because there's only 1 outgoing link from node 3. And plus what? There's no other terms. There's only 1 link pointing inwards to node 4. So we can just say pi 4 equals pi 3, and pi 1 equals pi 2. Now once we know that, the job is very simple now. Let's say pi 1 equals pi 2, this number is x. Pi 3 equals pi 4, this number is y. Okay. Now we know that there is 1 link from node 4 pointing to node 1. Right? But this node 4 is actually pointing outwards to 3 other nodes. So what we can write down now is that x equals y over 3. Okay. This is x, y, y. So just by looking at this arrow, we can write down x equals y over 3. At the same time, we also know that x plus y, so the summation of all the importance score need to be normalized. Let's say normalized to 1. Why do we need to normalize it? Because it doesn't matter what is the actual absolute magnitude. All that matters is the relative importance of one node relative to the other nodes. So now we've got 2 equations. One says x equals y over 3. The other says by normalization 2x plus 2y should equal to, say, a constant 1. Now we got 2 variables in 2 linear equations. In this case, we got a solution. The solution is x equals 1 over 8 and y equals 3 over 8, which satisfies our intuitive understanding in the last slide. Now, therefore, what we're going to output is that we will say nodes 3 and 4 tie for position number 1, 3 and 4, and nodes 1 and 2 tie for position number, I guess, 3, because positions 1 and 2 are tied between nodes 3 and 4. So you can display 3 and then 4 and then 1 and then 2, for example, on the search result page by Google. Now, is this the right answer or not? That's actually a tricky, almost philosophical question. What is the right answer? In some sense, the right answer depends on how does each user find the Google search results useful or not as useful. Now, because Google is such a dominant force in the search space today, it's actually hard to imagine what other search order might look like. So it's not easy to actually falsify whatever we might conjecture about that. And it is just very hard to measure or quantify subjective view on the usefulness of the search results. Okay. So what we are doing here is really a proxy of the real problem, which is make each individual users find the search results as useful as possible. And furthermore, as you can see that we carried out a whole bunch of computation. Well, in this case, it's not that much, 2 variables and 2 linear equations. But the actual numbers of these important scores are not displayed in the search result page. All you see is the rank order. You do not see the scale behind the order. So order is displayed. Scale, the numerical scale, is hidden from user's view. So in that sense, scale is really a means to the ends. So we don't know, for example, that this node is 3 times more important than that node. Now, these are some of the interesting caveats as we try to understand the true meaning of usefulness of search results. But for the rest of this lecture, we will just focus on computing this scale now, which translates as a special case into the order of presenting these results on the search result page. So now we have seen a very, very small example. The question is, can this computation be generalized to an arbitrary structure of the graph? And furthermore, can we efficiently compute when the graph becomes very big?